Hello. Okay, well today it's the last topic in this unit where we're finding derivatives of other functions. We found the derivatives of log functions, of exponential functions. Today we want to find out what are the derivatives of the inverse trig functions. So just to start out, I want you to think about your 6 normal trig functions: sine, cosine, tan, secant, cosecant, cotan. If we were to switch the x and y coordinates of every point on each of those graphs, we would get the inverse trig function graphs. And I put these up here for you. It's been a while, probably since you've seen them. Because the trig functions are not one-to-one, we couldn't switch the x and y coordinate of every single point on the graphs because then we wouldn't get a function. So for sine, we only looked at it from negative pi over 2 to pi over 2. So we just take that part of the sine graph, that is one-to-one. And when you switch the x and y coordinates, you get the inverse sine graph. Right? And same with inverse tan. We're just taking one part of, we're taking the tan graph, only looking at it between negative pi over 2 and pi, and just switching the x and y coordinates of those points, and we get the inverse tan. And it's not really that important, you know what they look like, but since we're going to find the derivatives of them, I just thought it'd be nice to be familiar with them. For cosine, we're switching the x and y coordinates for all the points on cosine between 0 and pi. So where's my inverse cosine? Is this? All right. So for cosine, you know, it starts up here at 1, and then it goes down. Oops, I kind of ran into this. Sorry, it's live recording. Let me just do that again. Okay, so cosine, when the angle is 0, the cosine's 1, and then it goes down to 0 at pi over 2 and over here. So if you just switch the x and y for that part of the graph, you get the inverse cosine graph. All right, so we'll find the derivatives of these, and I'm just going to show you where these formulas come from. You don't have to know this, but don't tune me out because it's still kind of interesting. So we want to know what the derivative of the inverse sine of x is. So we're starting out with y equals the inverse sine of x, and what we want to find out is what's dy dx. This is our goal here. Well, one thing that we can do is we could take the sine of both sides, because we know how to take the derivative of that. So if we take the sine of both sides, we get the sine of y equals the sine of the inverse sine of x. But think about what happens when you take the composition of a function and its inverse. One undoes the other. So the sine of the inverse sine of x is just x. So what we still have, this is still an equation for the inverse sine, it's just we've written it differently. And while we're here, let's go ahead and label a right triangle so we can see the relationship between the angle y and x. Now remember, sine is opposite over hypotenuse. So even though I could make opposite 2x and the hypotenuse 2, or I could make the opposite 3x and the hypotenuse 3, I'm just going to be nice and simple. I'll make the opposite x and the hypotenuse 1. So now we have the sine of y equals x, or x over 1. All right, now let's get the derivative. That's our goal here. The derivative of sine y is cosine y times, I hope you're saying it, dy dx. All right, chain rule. The derivative of x is just 1. Remember our goal. We want to figure out what is the derivative of this function. We want dy dx. So let's divide both sides by cosine of y. So if we do that, we get dy dx equals 1 over cosine of y. Well, that's nice, but if you have the inverse sine of x, you'd like the derivative to be in terms of x. So let's go look at that triangle that we drew there and see how we could rewrite the cosine of y in terms of x. Cosine is adjacent over hypotenuse. So we're just missing the adjacent side. You know that leg squared plus leg squared equals hypotenuse squared. So the length of this leg is going to be the square root of the hypotenuse squared, 1, minus the other leg squared. Now I can write down what the cosine of y is in terms of x. That would be the square root of 1 minus x squared over 1. I don't need that. So the derivative of the inverse sine, we use a little negative 1 there, right? Function notation, of x is equal to 1 over the square root of 1 minus x squared. That's formula number 1. There are basically only 3 different ones. The other 3 are just variations on these. Okay, moving on to number 2. This time we want to find the derivative of the inverse secant of x. We want to figure out a way to get the slope of this graph. So we're going to do the same thing we did last time. Again, we want dy dx. That's our goal here for this function. So first step, we don't know what to do with inverse secant, but we can get rid of it. We take the secant of both sides. If we do that, we get secant of y equals the secant of the inverse secant of x. That's just x. So now we can find dy dx with that implicit differentiation. So the derivative of secant y is secant y tan y, we're not done, right, times, think chain rule, dy dx. And the derivative of x is just 1. So to get dy dx by itself, we'll divide each side by secant y tan y. So dy dx equals 1 over secant y tan y. We need to see what we can put in for secant y and tan y. We need to look at the relationship between our angle y, that's the right triangle, and x. The secant of y, we want it to be x. So we want secant, which is hypotenuse over adjacent, to be x. So we can make the hypotenuse x and the adjacent 1. Now, we just got to get that missing leg. The missing leg is going to equal the square root of the hypotenuse squared minus the other leg squared. Okay. So we get that the derivative is equal to the secant of y. Actually, we already know what that is. Secant of y, we know that is x. Or you could look at the diagram. Then times the tan of y. Tan is opposite over adjacent. So the tan would be the square root of x squared minus 1 over 1, or just the square root of x squared minus 1. Now, one thing just to make it a little trickier here, if you look at the inverse secant graph, you notice how the slopes are always positive? So we need to just put little absolute values here. Keep that slope positive. Alrighty, next one. Don't worry yet. I know you're probably worried. Just one more derivation to show you. Now we want to figure out what's the derivative of the inverse tan of x. So I bet you're thinking what to do already. That's right. Take the tan of both sides. So the tan of y equals the tan of the inverse tan of x, which would just be x. Let's go ahead and label our triangle now while we have it. So we want the tan of angle y to equal x. And tan is opposite over, so it's opposite over adjacent. So we want opposite over adjacent to equal x. So we'll label the opposite x and adjacent 1. Now, might as well get the missing side while we're here. To get the length of the hypotenuse, we would take the square root of leg squared plus leg squared. So it's going to be the square root of x squared plus 1. Okay, let's go get the derivative. We want to find the derivative of the inverse tan. So the derivative of the left side, derivative of tan of y, using the chain rule, would be secant squared of y times dy dx, derivative of the inside. And that's got to equal the derivative of the right side, which would be 1. Now we can go ahead and divide each side by secant squared of y. So dy dx equals 1 over secant squared y. Well, if you remember, the reciprocal of secant is cosine. So secant is 1 over cosine, and cosine is 1 over secant. 1 over secant. So another way of writing this would just be cosine squared y. Now let's fill in what that is in terms of x. The cosine of y, so we just got to figure out what would the cosine of y be and then square it. So if you look at our diagram up there, cosine of y, that's adjacent over hypotenuse. So let me just move this one. So adjacent over hypotenuse would be 1 over the square root of x squared plus 1. But remember, we want this squared. And so the derivative of the inverse tan turns out to be 1 over x squared plus 1. That's a nice one. Now, I have the justifications here for the other three, why they have their derivatives. But here's just to make it real short, if you care. The angle whose cotan is x, the inverse cotan of x, is just pi over 2 minus, it's the complement of the angle whose tan is x. So if you took the derivative of both sides, the derivative of pi over 2, let me just move this down here, would be 0. And then we know what that is, so what we'll wind up with, it'll just be negative 1 over x squared plus 1. So if you can remember that the derivative of inverse tan is 1 over x squared plus 1, derivative of inverse cotan is negative 1 over x squared plus 1. It's just the same thing, but it's negative. And that's how it works for the other two also. And so I'm just putting them all up here so you can see them all at once. Okay, so we showed the ones that we've actually worked on. We did this one, derivative of inverse sine of x is 1 over radical 1 minus x squared. We derived the derivative of inverse tan of x. That's 1 over 1 plus x squared. And we also found the derivative of inverse secant x. That was a weird one. That was 1 over absolute value of x times the square root of x squared minus 1. The other three that we didn't really go through much, well, I did the one of them, they're just the opposites. So if you can memorize the derivative of the inverse sine of x, inverse derivative of inverse cosine of x is the same thing, but it's just negative. If you want to get the derivative of inverse cosecant of x, look at the derivative of inverse secant, and it's just negative. And then if you want to find the derivative of inverse cotan x, it's just the opposite of the derivative of the inverse tan of x. So it really is like you only have to memorize 3 formulas. I know it's still a little bit scary. The most popular ones are the inverse sine and inverse tan. If you notice, all the denominators have an x squared and a 1 in them, so you just got to be clear which is which. Okay, so here comes the good part. You know we can never settle with new formulas for derivatives of functions of x. We have to apply the chain rule. What if we're taking the derivative of an inverse trig function of u? Well, the derivative, the first one I have done for you. The derivative of the inverse sine of u is going to be 1 over the square root of 1 minus u squared times u prime. And what we do with these, we just tend to put the u prime up in the numerator. So we're just applying the chain rule I'm putting the u prime up there. So for the derivative of the inverse cosine of u, the inverse co-trig functions are the same as the normal inverse trig functions. You just negate them. The derivative will just be negative, and then same thing, u prime over square root of 1 minus u squared. Derivative of inverse tan of u. Well, just apply the chain rule. So if you remember, the derivative inverse tan of x was 1 over x squared plus 1. So the derivative of inverse tan of u is 1 over u squared plus 1, or 1 plus u squared, whatever you like. Same thing. But we have to multiply by u prime, which we can then put in the numerator. And so the derivative of inverse tan of u is u prime over u squared plus 1. Derivative of inverse cotan of u, same thing, but it's just negative. Derivative of inverse secant of u, okay, just applying the chain rule. So it's just like with the x's, but then we have to multiply by u prime, so we put that up there. And then the last one, derivative of inverse cosecant of u, same thing, but it'll be negative. So it'll be negative u prime over absolute value of u times square root of u squared minus 1. It's time for flashcards. But really, it's only 3 that you have to really memorize. All right, so let's try to do it. First example, we want the derivative of arc sine of 3x. That just means the inverse sine. It's just another way of writing it, 3x. So you got to think of the formula, the derivative of the inverse sine of u. So if I take the derivative of that, the formula is u prime over the square root of 1 minus u squared. In this case, our u is the 3x. So the derivative, in this case, is dy dx equals, u prime goes up top. Whatever you're taking the inverse sine of goes up in the numerator, so that's 3. And then in the denominator, we have the square root of 1 minus u squared. Well, u is 3x, so if you square it, you either leave it in parentheses with the squared, or you square it out, 9x squared. Okay, next one, derivative of inverse tan of x squared. So let's think of the formula for the derivative of inverse tan of u. Inverse tan of u, that's my favorite derivative. It's u prime, they're all u prime up top. But this is the only one without a radical down here. And there's a plus. The other ones are negative. And I always think of the plus because of the inverse tan. Reminds me. Okay, so this time, u is equal to x squared. So our derivative, dy dx, equals, the numerator is always u prime for these. So u prime, the derivative of the argument, the inside function, should have 2x. Now in the denominator, we need u squared plus 1. U is x squared. So u squared would be x squared squared, or x to the 4th plus 1. Uh-oh. This time, we have an inverse cosecant, so let's write down that formula. The derivative of the inverse cosecant of u, so the inverse cosecant u prime, is equal to, remember, the inverse co-trig functions are negative, negative u prime over, then it's absolute value of u, square root of u squared minus 1. It's easy once you know the formulas. Okay. U this time is sine x. So the numerator of our derivative has to be negative u prime. All right. So derivative of sine is cosine. So we have negative cosine of x over absolute value of u. So it's just the absolute value of sine x times the square root of u squared minus 1. Square root of u squared, so that's the sine of x squared, but you can write sine squared x minus 1. Okay. Example D. Now this time we don't just have the derivative of an inverse trig function. It's there, but it's within the product rule. But I will write down the general rule over here for the inverse cotan derivative. The derivative of the inverse cotan of u. Now it's an inverse cotrig function, so it's going to be a negative u prime up top. And for the denominator, it's u squared plus 1. But again, we're not just going to do that because we're not just taking derivative of inverse cotan. All right, we have a product rule we have to take care of. So we'll get to that. So dy dx first x times derivative of the second. That's the derivative of inverse cotan of x. Now this time our u is just x. So we're just going to have negative, the derivative of x is 1. The denominator, we need u squared, so that's just going to be x squared plus 1. So far we have first times derivative of the second, and then we have plus the second plus the inverse cotan of x times the derivative of the first. Now, if you want to put that x up in the numerator, you want to write it as negative x over x squared plus 1 plus the inverse cotan of x. That would look nicer. Now, look at example E. I could write down the formula for the derivative of the inverse cosine of u and do that. But look at it. Are you looking at it, kids? All right, I hope you're looking at it. Can you simplify that? You have a composition of a function and its inverse. The inverse cosine of the cosine of x, why, that's just another way of saying y equals x. Whenever you take the composition, you're plugging of a function and its inverse, you're plugging one of them into the other, into the x of the other one. One undoes the other. So getting the derivative for this one is as easy as getting the derivative of x, so it's just 1. So we kind of got away with it that time. The next one, we are going to have to know this is the derivative of the inverse secant of, and you know, I want to put parentheses. That we're going to replace the square root with the exponent of 1/2. And you know we're going to be applying the chain rule, so let's put parentheses around all that. So we're going to be taking the derivative of the inverse secant of the quantity 1 plus 2x squared to the half. Okay, so originally our u is all this. This is our u. All right, it's the argument for the inverse secant. And I have to recall that the derivative of inverse secant of u, so inverse secant of u prime equals u prime over the absolute value of u times the square root of u squared minus 1. Okay, so let's do this. Now, Maybe we'll do the denominator of our derivative first. So the denominator, it's the absolute value of u. Remember, our u is just the square root of 1 plus 2x squared. I think I'll just write it with the exponent. 1 plus 2x squared to the half. You could just write the radical there also. So it's the absolute value of that, absolute value of u, times the square root of u squared minus 1, times the square root. If you square something to the half, it's just to the first. Or if you square square root, okay, one undoes the other. So if you square 1 plus 2x squared all raised to the half, you just get 1 plus 2x squared. That's our u squared. And then it's minus 1. So far in the denominator, I have the absolute value of u times the square root of u squared minus 1. Now I could get rid of those 1's under there. But let's talk about the numerator, which has to be u prime. To get u prime, we're going to have to use the chain rule, because u is a composition of functions. So the derivative of the outer function first, 1 half 1 plus 2x squared to the negative 1 half, times the derivative of the inside. So times 4x. Now, I don't know about you, that just doesn't look so good. Well, you know, you could get rid of these, but we're not going to worry about the simplifying. I want to keep focused on this. And then you could, now let's just leave it. Let's leave it. Next one. We have y equals 1/3 the inverse tan of x squared over 4. So think about it. Do I really need to use product rule here? No. First factor is a constant. So when we go to find the derivative, it'll just be 1/3 times the derivative of the inverse tan of x squared over 4. So let's recall the derivative of the inverse tan of u. So that prime equals, hope you get the numerator right, u prime over, this is the one with the plus and no radical, u squared plus 1. All right, so to get the derivative of our function, dy dx, this 1/3 here, it's a constant multiplier. It's not just 1/3 plus, because then the derivative would be 0 plus. 1/3 times. It's like you're doing first times the derivative of the second part drops out. So I'm going to leave the 1/3 and multiply by the derivative of the inverse tan of x squared over 4. So this time our u is x squared over 4. So its derivative, u prime, the derivative of x squared over 4. If you think about it, x squared over 4 is the same thing as 1/4 x squared. So its derivative is 2 times a fourth, or 1/2 x. 1/2 x, or x over 2. That's my u prime. And then we need down in the denominator u squared plus 1. U is x squared over 4. We're going to square that. So you could just leave it in parentheses squared, or you can write x to the 4th over 16, and then plus 1. So it's 1/3 times all that. 1/3 u prime over u squared plus 1. I hope you enjoyed this, and be good. Just try to do some of these homework problems. All right, bye. Wait, I don't think that is when I wanted to say bye. Never mind. Wait, let me check that out. No, I didn't want to say. Sorry, that was I went too soon. Forgot my summary. Write down the derivatives of all 6 inverse trig functions of u. So the ones without the cos, you know, that are not coming from complements of other ones, those, they're all positive. So they're all going to just have regular old u prime up in the numerator. And really, the only thing that's different are the denominators. The denominators are all going to have a u squared and a 1. You just got to remember which is which. For inverse sine, it's square root of 1 minus u squared. For inverse tan, the denominator will be u squared plus 1, or 1 plus u squared. The inverse secant, that's the weird one. That's the absolute value of u times the square root of u squared minus 1. If you know those, then the derivatives of the inverse trig, co-trig functions, same thing but just negative. So derivative of inverse cosine of u is just going to equal negative u prime over the square root of 1 minus u squared. The derivative of inverse cotan of u is going to equal negative u prime over the square root of u squared plus 1. And derivative of inverse cosecant of u is negative u prime over absolute value of u times the square root of u squared, minus 1. Oops. Now, if you were sleeping up until now, wake up and take a look, because this is all you have to know. Really, this is all you have to know. You just got to be able to apply these formulas, along with all your other rules, product rule, quotient rule, and all the other derivatives. All right, so hopefully with the observations here I'm talking about, realize that those inverse co-trig functions, those are all negative. Also, all the numerators are u prime, and all the denominators have a u squared and a 1 in them. So sometimes when you compare, it helps you to memorize which is which. All right, that, I believe, is the end. Yes.